But today we're looking at optimization, and which is a nice callback to last week, because we talked about this concept last week. Optimization means finding the max and finding the min. And so we talked about absolute max and min last time versus local max and min. We have the extreme value theorem, which guarantees that if you're continuous on a closed bounded interval, you will get your maximum and you will get a minimum. Where could those happen? If we're on a closed bounded interval, they could happen at the endpoints or they could happen in between. If they happen in between, they're going to be local maxes and mins. And Fermat's theorem helps us figure out where those could be. You follow? And so last Monday, we kind of came up with this scheme, optimizing continuous functions on closed bounded intervals. And you did a couple of these on your take-home and your test as well. Okay, so hopefully this is fresh in your mind. So today we're going to be looking at applications, aka word problems, where we're going to be trying to find either a max or a min or both. And in some cases, when we put together the mathematical model for the situation, we'll have a continuous function on a closed bounded interval, and we're good to go. However, sometimes we won't. The function that we're optimizing may not be continuous, or in the cases we'll be saying, we might be looking at an unbounded interval, so we might be looking at an open interval. And so what happens there? So we have this nice little property, and enjoy this while it lasts, because this is one of those things. There's a lot of what we do in Calc 1 that gets nicely generalized to multivariable calculus. How many of you have to take multivariable calculus at some point? It varies now who takes it. This is one thing that doesn't generalize very well at all. It's called the lone critical value. So here's the idea. Suppose f is continuous on, say, an open interval. And f has precisely or exactly one critical number in the interval. So it's got only one critical value. So we've got this continuous function. It does its thing. We got some open interval down here. So, you know, it only has one critical number. That means that if I, when I go to connect the dots, it can level off or have a sharp turn like only once. So like that maybe. Oop, I'm not doing this really well today. So say that's the critical number there. Okay. Let's call this critical number C. If f of c is a local max, then f of c is the absolute max. And analogously for min. So if you have only one critical number and you got a local max, that's got to be the absolute max. Now, why is that? Let's say you've got let's say that's where the thing is 0 and it's a local max. So I know that it's got to look like this. Oops. If it weren't the absolute max, and that means there would have to be some y value elsewhere that's bigger than that y value there. You follow? Now, if the function is continuous, what has to happen? You have to be able to connect these dots without doing any jumping or asymptotes. You follow? So what's going to happen? At some point, to connect these dots up, it has to do what? It has to do some kind of turning around. You follow? And where you turn around, if it's a gentle turn or if it's a sharp turn, either way, you're going to have another critical number. You're going to have a place where if you have a sharp turn, the derivative doesn't exist. If you have a gentle turn, the derivative would be 0. And that would contradict that you have only one critical number. Does that make sense or not? Okay, so that's the lone critical number. And we'll see this in one of the examples we do today as well. So this is what we use. If on the interval, let's say it may not be, maybe it could be not bounded, or maybe not closed. So like let's say you're trying to optimize a function for positive values x, something like that. Okay. All right, and just like we had a section on related rates, I don't know, a week and a half ago, maybe. Section 3.9, these are guidelines for working applied problems. There's no one single recipe that works for all of them. But since we're trying to optimize, we want to figure out what we're trying to maximize, or I guess that should be an or minimize. All right, that's what we typically call the objective function. So we're trying to maximize profit, we're trying to minimize cost, are we trying to maximize surface area, are we trying to minimize volume, what are we trying to do? And then assign variables as needed. And use formulas, often from geometry, to relate the variables to the objective function. And once again, keep track of units. A lot of times units will let you know if the expression you have makes sense. Right? Like if you're trying to optimize a volume, say find a minimum volume, then you would have to have cubic units whenever you put all your stuff together. You want to make sure your objective function is a function of just one variable, okay? Because we're in single variable calculus. Then you want to determine a reasonable applied domain. All right? So like if you're, for example, you're building a fence, it doesn't make any sense if you have negative dimensions for that fence. You follow? The fence needs to be negative 5 foot long by 2 foot tall. That doesn't make any sense. You follow? If your applied domain is a closed bounded interval, then you can just do exactly what we did back in section 4.1. All right? Find the critical numbers, plug the endpoints and the critical numbers into the function, biggest number max, smallest number min, like the stuff you did on the take-home and the test. Otherwise, try using the curve sketching stuff that you know about, in particular, the lone critical value property. All right, so the way I like to do this section is we're going to pick 3 homework problems to do from the text. So we'll have those up here. We'll work through those. They kind of showcase different things that can happen in these problems. And then, of course, I've got 2 videos for you, a little more involved problems. So example 1 and example 2, which showcase other techniques and methods. Okay. One of these is a closed bounded interval. One of these is an open interval, so you can see how to what goes on there. All right. So let's take a look at these problems in the book. I've got the book here virtually. So section 4.5. This is where your homework's going to be. So we want to take a look at number 16. This is classic. There's a good bless you. There's a good chance you encountered this sort of thing back in pre-calculus in some kind of algebra class. So we're trying to build a rectangular pen with one side against the barn. 200 meters of fencing are used for the other 3 sides of the pen. What dimensions of the pen maximize the area of the pen? Okay? So the first thing we're doing is, what are we trying to optimize? In this case, the optimization, remember optimize means maximize or minimize. We're trying to maximize the what? Area of the pen. So let's sketch this out. So we've got this barn, which is that way, and we're going to build a rectangular pen. So we'll do that. Okay. All right, so we need to introduce variables here. We want to introduce variables here. So in order to figure out the area, that's our objective function. What letter do you want to use for area? And how do I calculate the area of a rectangular pen? Length times width. All right, so we call this length and width. So area is length times width. And what letter do you want to use for length? L. And width? W. And everything here is going to be measured in what? So let's take a look here. In this problem, everything's being measured in meters. You follow? So we would have, if I look at units, I'd have meter times meter, which would be meter what? Squared, which makes sense because it's an area. You follow? All right. Now the problem we have right now is what? We've got the area in terms of two variables. You follow? We need it in terms of just one variable. Okay? So I need to figure out a relationship between L and W. So let's go back to the word problem. What else do they tell us? The pen is with one side against the barn. 200 meters of fencing are used for the other three sides of the pen. You follow? So this is going to set up a relationship, a constraint between the L and the W. All right. So how would you formulate that constraint? So what's the relationship between L and W? If you have 200 meters of fencing left over for this, what would it be? 2W plus L has to be 200 meters. Make sense or not? Right, so I've got 200 meters of fencing, and that's got to be for this side plus this side plus this side, so we get to there. We all cool with that? And now what we want to do, so once again, if we sort of take a step back here as we're going through here, this is our objective function. This would be considered our constraint. Now we want to use our constraint to get our objective function in terms of just one variable. So I'm going to copy this to the next page. I've got A equals L times W, but I know that 2W plus L has to be 200. So how can I use my constraint to get the A in terms of just one letter? What can I do? So I can solve this equation for either L or W. Let's say I solve it for what? L. So L would be 200 minus 2W. And then what can I do with this expression for L? I can plug this back into there, and now I have an expression for the area in terms of the width. And if I go ahead and simplify this, I now have area as a function of W. So oftentimes you'll see this A equals A of W is minus 2W squared plus 200W. So this is just function notation. This says that the area is now a function of just W, as opposed to here, the area was a function of length and W, or length and width. Now we've got it down to just a function of one variable. So this, when you see stuff like this, remember, it doesn't mean multiplication. We're not multiplying the area times the width here. We're saying that the area can now be directly computed by the width. So for example, if you choose your width to be let's say 50, then this would tell you what the area is directly, right? Because if W is 50, then 2W is what? 100? 200 minus 100 times 50? 5,000. So that area would be 5,000 square meters. You follow or not, folks? Okay. All right, so we now have the objective function in terms of just one variable. Now we need to figure out an applied domain. So this is where we have to think, what values of W are going to make sense in this particular situation? So we go back to what's happening here. We got originally our W and our L. To even have a pen, W and L have to be what kind of numbers? Positive. So I'm going to need W to be bigger than 0, which, okay, I can do that. But I also need L to be bigger than 0. And you notice we don't have an L up here anymore. You follow? And the reason is because we use this relationship. You follow? So L being bigger than 0 is the same as 200 minus 2W being bigger than 0. And if 200 minus 2W is bigger than 0, then that means minus 2W has to be bigger than minus 200. And if I go to solve for W here to see what other condition we have on W, what would I have to do to both sides? Divide by the negative 2. And when you divide by a negative, what happens to the inequality? Yeah, it flips around. So that's going to change this. So now we would get W less than what? 100. So now both of my conditions involve W, so I know that W is between 0 and 100. You follow or not, folks? Now, technically speaking, is this a closed bounded interval? No, I don't have the endpoints. Could I include the endpoints? If I actually let W equal 0, or if I let W equal 100, well, let's go back to here. If I let W equal 0, the area would be what? 0, which we know we wouldn't care about. If I let W equal 100, the area would be what? 0, which I know it could, So I could tack on the endpoint since I know I'm looking after a positive value. You follow? Or we can use this as a place to look at our lone critical number. But yeah, this would be the problem then. This would be the mathematical model for what we're doing. And there's a good chance you did this kind of thing in algebra, because can you tell me what kind of graph this is going to be? What kind of function do we have here? Yeah, it's a quadratic, so its graph's going to be a parabola. So you often would solve this by using vertex formula stuff. You follow? The nice thing about calculus is you don't need to worry about memorizing the vertex formula anymore, because you can always get it by taking the what? Yeah, let's take the derivative. So let's go looking for critical numbers here. What's the derivative? What's a prime of W? Negative 4W plus 200. Are there any places where this derivative won't exist? Any zeros in the denominator we got to worry about? So I'm going to set that equal to 0. So minus 4W is minus 200. To solve for W, we do what? So what do I get for W? 50. Okay, now let's do a quick check. Is that in our domain? Is that a yes? That is there, and moreover, is there any other critical numbers? No. Okay, so W equals 50 is the lone critical number. So let's see what's going on. Let's see if it's a local max or local min. There are two ways we could find if it's a local max or local min. We could use the first derivative and check around it to see if it's increasing then decreasing. Or, what's the other way we can check? We could look at the second derivative, which is really quick to get here. What's the second derivative here? -4. And so what does that tell us? Graphically, that means that this graph is always what? Second derivative is negative, it's concave. It's concave down. And we know that at 50, it was flat. So by the second derivative test, we know that 50 comma a of 50 is the local max. And then by the lone critical value property, we know it has to be the absolute max. Do you see how those two concepts help us out here, folks? Now let's go back and see what they actually wanted in the problem. They say, what are the dimensions of that maximize the area of the pen? Okay? So they want the dimensions of the pen. So the dimensions of the pen are the what? That's the width and the length. You follow? So the width we already know is 50, and that would be 50 what? What's the units here? Meters. And how can I figure out the length? Well, this is what's nice about what we did here. We've got the length in terms of the width. You follow? So the length is 200 minus 2w. So 200 minus 100, that would be 100. So 100 meters. So the dimensions would be 50 meters for the width, 100 meters for the length. So to be specific, because there's a difference here, the best way, I guess, to communicate that to the farmer would be to just create that diagram. Make sense or not? Now, one thing they didn't ask about is, well, what is the maximum area? They didn't ask for that, but what would it be? Just 50 times 100, so what, 5,000 square meters? They didn't ask for that. So when you're looking at these problems, you want to make sure you answer all the questions they ask. Okay. Any question on the setup here? You typically are going to start with a picture. Use geometry to relate the variables. There's usually some kind of condition. You want to eventually get your objective function in terms of one variable. Then you want to come up with an applied domain. And then you want to use calculus on it. You follow? Let's take a look at part B. So now I got a rancher plans to make 4 identical pens, identical and adjacent rectangular pens against a barn, each with an area of 100 square meters. What are the dimensions of each pen that minimize the amount of fence that must be used? Okay. So now, instead of telling us how much fence you have, maximizing the area, now they're telling us what the area should be. We're trying to minimize the amount of what? Fencing. Okay. So this, once again, they're being built up against a barn. identical and adjacent pens. So they have a little picture for us already. It's always nice when they these are all supposed to be identical. And they want each of these things to be 100 square meters. They want to minimize the amount of fence. So once again, optimization means minimizing or maximizing. And here they're trying to minimize the what? They want to minimize the amount of fencing. Oops. So what do you want to call the amount of fencing? Call that F. And how would I calculate how much fencing? They're looking for the what? The dimensions of each pen. So once again, what we have control over are the what and the what? The what? So what do you want to call this side? Width or length? Length? It looks like it's going to be longer. So then this would be the what? Width. And so this would be the length again and the width. The length again, the width, the length again, the width, the length again. So how many lengths, how many L's do we have up here? 1, 2, 3, 4, what? 5L. And how many W's do we have up there? Now once again, length and width are going to both be measured in meters, so I have an amount of meters plus an amount of meters. That would give me an amount of meters, so it makes sense based on what the unit should be here. So this is our objective function. So now what I need is I need to figure out a constraint. I need a relationship between the L and the W. What do they tell us about each of these pens? The area is 100 square meters. So that means that what? How do I get the area of each of these individual pens? Length times width. That has to be what in this case? 100. So I could solve this for either L or W. Let's solve it for L. What's L going to be? (100 over W). And so what can I do with that now? I can take my 100 over W and plug it in where? And now I can get my fencing as a function of just the width. That's going to be 5 times 100 over W plus 4W. So I have 500 over W plus 4W. So that's our objective function. Now, the thing is, if you start freaking out about units, don't. Because that 100 has a unit attached to it. That's 100 what? Meters squared. So that meters squared divided the meters. This is still going to give you meters. You follow? That we're adding to more meters to get meters. Okay, now we need to look for the applied domain. So in this particular scenario, what values make sense? Well, once again, we're trying to create pens. So the width has to be what kind of number? Positive. And the length has to be what kind of number? It has to be positive. My objective function only has W's in it. Let's go back and look what the L is. L is 100 over W. Well, that really doesn't give us any new information, does it? Okay. So here's an example where not only do we not have a closed interval, in the last example, we didn't technically have the endpoints. Here, we're on an unbounded interval. You follow? So once again, we're going to have to use the lone critical number stuff. Hopefully that applies. So now we're off and running. So here's our f of w. Uh, 500 over w plus 4w. We're looking for w bigger than 0. And now we're off to look for critical numbers and see what's going on with that. Oops. So I got to take the derivative with respect to w here. How can we rewrite this to make the derivative as easy as possible? How do I write it to avoid the chain rule or the quotient rule? What can I do? This would be 500w to the minus 1. So now we should be good to go. What's the derivative of 500w to the minus 1? Minus 500w to the negative 2. What's the derivative of 4w? 4. And we want to look for critical numbers. Are there any places here that would make this denominator undefined? Yep, w can't be what? 0. But do we care about w as 0? No. Okay. So now we'll set it equal to 0. Negative 500 over w squared is negative 4. So negative 4w squared is negative 500. So what's w squared equal to? 125. And how do I solve for w then? W would be what? Plus or minus the square root of 125. Which I could simplify. Is there any perfect squares sitting inside 125? Yeah, it's 25 times 5, right? I can bring some of those out. There you go. Now, which of these do we care about? Our applied domain, we're looking at w what? Bigger than 0. So which of these do we care about? That one. Which means we have found exactly how many critical values in the interval we care about. We found only one. Okay? So now let's go to the second derivative to see, do we get a maximum or a minimum? What would the second derivative be? Thousand w to the what? Minus third. And what's the derivative of 4? So let's take a look at the derivative at our critical value, 5 root 5. I don't have to know the exact retail value of this to hit it with the second derivative test. I just need to know, is it going to be positive or is it going to be negative? I'm plugging 5 root 5 in, which is a what? So this is going to be what kind of number? Positive. So on our graph, over here at 5 root 5, I know that the first derivative is 0, so I know that it's locally flat. The second derivative is positive. That tells me it's concave what? Up. Okay. So the second derivative test says that 5 root 5 comma whatever the function value is there is a local what? If it's concave up and flat, it's a local min. And then the lone critical value property says that not only is it the local min, it's the what? It's the absolute min as well. So once again, you see how those two concepts pair off together? So I go back and look at what they want. What are the dimensions of each pen that minimize the amount of fence used? So once again, they don't care what the minimum amount of fence is. They want to know what the dimensions will be. Okay, so we found to minimize fencing, we found our width to be 5 root 5 meters. So once again, let's draw a picture for the rancher. So that's 5 root 5 meters. Now I got to figure out this. That's our length. And what was our formula that related the length to the width? Yeah, it's 100 over that. We'll do a little bit of algebra here. 5 goes into 100 how many times? 20. And then, you know, it depends how you want to proceed here. You could factor the 20 down, or you could rationalize if you want. We get 20 root 5 over 5, or 4 root 5 for that. Okay. So those are the dimensions. Make sense or not, folks? So just like all word problems, you start off, sketching a diagram is often helpful. In this case, they gave us a diagram. Labeling the variables, this means this, this means this. This is how those variables are related. This is how they tie into what we're trying to optimize. And then you go through and do what you did, what you learned last week on it. Make sense or not? Let's actually check this one. Just to remind you how so let's write our f. Once again, we'll turn everything into x's. We only care about x's that were positive here. And what was our function? Our fencing function was 500 over x plus 4x. We're looking at f of 5 square root 5. So 89, that's supposed to be the minimum. So here, if we want to go over here, let's get a 5 root 5 approximation as well. So this helps us set our window. So since the x we're looking at is like, I don't know, 11, let's go from like 0 to 20. And the y we're looking at is roughly 90. So let's go, I don't know, 50 to 100. All right, there we go. Boom. Make sense or not, folks? And if we zoom out, okay, looks like we got a nice little what here? Slant asymptote. Can you see what that slant asymptote would be? As x goes to infinity, what happens to this 500 over x? Just goes to 0. So what's left? There's another slant asymptote for you. All right. So those are classic pen problems. There's lots of different variations of those. Let's move on. Now we're going to look at number 22 from the book. And once again, you'll have two problems to look at with videos. Closest point on the line. This is a very mathy problem that has applications later on. Because oftentimes, like if you go on and take a class called linear algebra. Linear objects, mx plus b's, and then the generalization of linear, which happens later. Linear things are typically things that we can easily find solutions to. Right? That's why we love derivatives. If a function is differentiable, it means it's locally what? Linear, and we understand how lines work and all that good stuff. But sometimes what happens is you have your ideal solution, okay, but that doesn't work in the context of the problem. So you end up trying to figure out, okay, well, what's the best I can do? You follow? So that kind of thing comes up here. We got the closest point on the line. What point on the line y equals 3x plus 4 is closest to the origin? So maybe 3x plus 4 is what we're allowed to work with, and it's the origin we're trying to get to. Is the origin on the line 3x plus 4? No, because when you plug in 0, what do you get? 4. You don't get 0 out. So we're trying to see, okay, what's the best we can do? What's the closest we can do? So once again, we'll sketch the situation. There's the origin. There's your line, y equals 3x plus 4. And we're trying to figure out the point on the line that's closest. So we're trying to minimize distance. Oops. That's what we mean by closest. So minimize distance. All right. So how do we measure the distance between 2 points in the plane? So if I have a point here, x comma y, and I got the origin here, 0 comma 0, how do I measure the distance from a point on the line to the origin? Hey, little Pythagorean theorem here gives us the distance formula. There it is. Now once again, the problem is that that's a function of two variables. We want to get it to a function of what? One variable. So what's the relationship between x and y that we've got going on this line? Oh, that's nice right there for us. You follow? So we'll go ahead and plug that in. So the distance as a function of x would be the square root of x squared plus the quantity 3x plus 4 squared. So here we're using the constraint right there. So our distance is our objective function. Here's our constraint. Do we have any restrictions on x? I mean, we've got that entire line to think about, right? So we're good. That's it. So off to the races. Let's calculate the derivative here, d prime of x. I need to take the derivative of this. How would you, what's the first thing you would do to take the derivative of this? Instead of looking at that big old square root, you'd rewrite that square root as a what? 1/2 power x squared plus 3x plus 4 squared. And now what's the derivative of something to the 1/2 power? So what's the derivative of something to the 1/2? That's what? 1/2 times on something to the minus 1/2 times its what? Derivative. So we'll go back to that. 1/2 times all of this. That's 1/2. times the derivative of what's inside. So I got 1/2 times all of this. And let's see, what's the derivative of x squared? 2x. What's the derivative of something squared? Be 2 times that thing to the first times the derivative of that thing. And what's the derivative of 3x plus 4? What's that? 3? So far so good taking the derivative. Okay, now we notice we got a negative exponent there, so we're going to have to put that where it belongs, which would be down in the denominator. We're going to have a denominator. I got a 2 down there already. And I got all this thing. And then in the numerator, I've got 2x plus, and then let's go ahead and clean this up, because I'd have 3 times a 2, which would be what? 6 times 3x would give me 18x, and then I got a 3 times a 2, which is 6 times 4 is 24. So that's a 20x plus a 24 over this. And now there are no restrictions here on x. So let's take a look to see if how many critical numbers we get and where they are. Is there any chance that the derivative would not exist? Let's take a look at that. Let's look at this denominator here. Is there any way for that denominator to be 0? Well, let's think about it. The 2 can't be 0, so we don't have to worry about that. Anything you plug in for x, what's going to happen? It's going to get squared, right? That's going to make it bigger than 0. You plug it in here, this is going to get squared, right? So that's bigger than 0. Can this ever actually equal 0, though? Well, if it did equal 0, I mean, this is the distance, you follow, to the line. And does the line go through the origin? No, so it can't. So this will never be 0. So this is never 0. Or else the line would contain the origin. Off to chemistry? What are you working on today? Titration? Ah, it's one of my favorites. So the only other place then is to get critical numbers is if we set this whole thing equal to 0, which means we really are setting the what equal to 0. Okay. So if we set 20x plus 24 equal to 0, what do we get for the x? So subtract off the 24, divide by the 20, simplify that down, you get minus minus 6/5. Okay. Now, once again, this is the only critical value. Right. So we have an unbounded domain. We can't use what we learned last week. So we're going to have to rely on the lone critical value property. So we want to know, the question is this thing a local max or a local min? Now, on the last two examples, the second derivative was easy enough to get, and we could just take the second derivative, check concavity, and we're done. You follow? But here's the first derivative. You follow? Do you want to take the second derivative of that? No. So we can fall back and look at the first derivative. So this would be a case where let's do the first derivative test. So the first derivative test, we got our x's down here. We're going to look at our derivative here. Negative 6/5 is where the derivative is 0. Now we're just going to plug in some numbers around here to figure out what's going on. And we've already argued that the denominator here is always going to be a positive number because it's a distance from a line that doesn't go through the origin to the line. So it's always a positive number. So really we just have to focus our attention on the what? So if you plug in a really big x value, like I don't know, negative 100, that numerator is going to be what kind of number? Positive or negative? If I plug in a number bigger than negative 6/5, like 0, that numerator is going to be what kind of number? Positive. And sure enough, what does that mean about the function itself? A negative first derivative means all the slopes are negative, so it means it's what? Decreasing. And then at negative 6/5 it does what? Levels out, and then it's what? Increasing. So sure enough, what kind of feature does that make there? A minimum. And since it's the only critical number, we know it has to be the absolute minimum. So the first derivative test tells us that the point negative 6/5 d of negative 6/5 is a local minimum. The lone critical value property tells us then that this is the absolute minimum. And now we go back to see what they're asking for. Are they asking for the distance to the line? Or are they asking for the point closest to the line? Let's take a look at what they're actually asking for. Whoops, didn't mean to do that. Here we go. So what are they asking for in the problem? They're asking for the point on the line that's closest. So they don't care what the actual distance is, they just want the closest point. Okay. So the closest point is an x comma y. The x we know is negative 6/5. How do we figure out what the y is? Yeah, we go back to that constraint. I know that y equals 3x plus 4. So I'll plug in the negative 6/5. I got a minus 18/5 plus a 20/5. So that's going to be a what? 2/5? Make sense or not, folks? So as far as Desmos, and I want to point something out to you here. I'm going to check this a different way. Let's actually put that line in, 4x plus 3. Is it 3x plus 4? Oh, 3x plus 4. That's why. It's the wrong function. There you go. That's on the line right there. Okay. Now I got a question for you. Let's look at the line from the origin through that point. So what would be the equation of that line? So what would the slope be? If I wanted to figure out the equation of the line, there. So what would the slope be? So it'd be the change in y, which would be negative 0.4 over the change in x, 1.2. We'll just leave it like that. And then the x and y intercepts are 0. So we'll just do that. Boom. Okay. What do you think this angle is between these two lines? It should be what? It should be perpendicular, you follow? Because if you think about it, we're trying to figure out the point on the line closest to the origin, which means that the angle should be a what? 90 degrees. Make sense? We can actually check that. The slope of this line was, well, negative 2/5 over 6/5. The 5's cancel, negative 1/3. That's the exact, the slope up here is 3. And what do you know about lines that have negative reciprocal slopes? The lines are what? Perpendicular. You follow or not? So another way we could have done this problem without calculus is we could have just figured out what the slope of the other line had to be and then figure out where that new line would intersect. Does that make sense or not? So that'd be an algebraic way to do it. Just want to point that out. All right, what was the last one we wanted?